Hi, welcome to 24 Hours of Past, 20 years of past learnings, and future vision. We're excited you could join us today for Gail Shaw's session, The Once and Future Self-Tuning Database. This 24 Hours of Past consists of 24 consecutive live webinars delivered by expert speakers from the past community. The sessions will be recorded and posted online after the event. You will receive an email letting you know when these are available. My name is Todd Salzman. I have a few introductory slides for you before I hand the reins over to Gail. Next slide, Gail. If you require assistance, please type your request into the questions pane located on the right side of your screen, and someone will assist you. This question pane is also where you may ask any questions throughout the presentation. Feel free to enter your questions at any time, and once we get to the Q&A portion of the session, I'll read your questions aloud to the speaker. You are able to zoom in on the presentation content by using the zoom button located on the top of the presentation window. Please note that there will be a short evaluation at the end of the session, which will pop up after the webinar ends in your web browser. Your feedback is really important to us for future events, so please take a moment to complete this. Next slide. I'd like to take a moment to thank our sponsors, Microsoft and Intel. The staging of 24 Hours of Past wouldn't be possible without their generous support, and they are the reason this event is available free of charge. If you would like to learn more about Microsoft or Intel and sign up for information on how they can help you, please visit the sponsors page of the 24 Hours of Past website. Keep learning all year long with PASS. Visit pass.org and check out all the free educational resources available to PASS members. Also, don't forget that PASS Summit 2019 will be happening on November 5th in Seattle, Washington. Head over to passsummit.com and register today. This 24 Hours of Past session is presented by Gail Shaw. Gail holds a Microsoft Certified Master certification for SQL Server 2008 and is a data platform MVP. She is a database specialist focusing on database performance and tuning and database recovery, with a particular interest in topics such as indexing strategies, execution plans, and writing T-SQL code that performs well and scales gracefully. And without further ado, here is Gail with the Once and Future Self-Tuning Database.
All right, hello everybody. So I'm going to be taking you through today some of the new features, well, kind of new features, some of the stuff that's in SQL Server 2017 and some of the stuff in 2019. But I was told that this is the past learnings and future vision session, so let's have a little bit of history first. I don't know if anybody watching is old enough to remember this, but way back when Microsoft was releasing SQL Server 7, I should mention that's 1995 era. Sorry, 7 was a little bit, it was 1998, but this is the mid to late 1990s. They made a very big deal about SQL Server being a self-tuning database system. It wasn't. It was a nice attempt for the time, but it was anything but self-tuning, unfortunately. Basically, what SQL 7 had in it was memory management. You didn't have to tell it how much memory to use. You gave it ranges, and the database engine could adapt. It had the automatic updating statistics with the execution plans that the query optimizer could generate from those stats. And it could work out by itself how many processes to use when it ran in parallel. Unfortunately, that was marketed a little bit too hard, and a lot of people believed that it really was a self-tuning database, which it really wasn't. And there was a lot of reputation problems that came from that, from SQL 7 being labeled a little bit more self-tuning than it might have been. So that message has been dropped by marketing for quite a while. But if we fast forward almost 20 years, what we have in SQL Server 2017 is a feature, or a set of features, I should say, called intelligent query processing. Now, again, this is a little bit of a marketing thing because they're not actually intelligent. There's no AI, full-on AI under the covers going into this, not yet anyway. But we do have at least a few steps towards intelligent query processing. And one hopes that the marketing of this will not be quite as badly received as the SQL Server marketing was. So what falls underneath the intelligent query processing is the following. We've got something called adaptive joins. This is in SQL 2017, and this was introduced partially to address bad parameter sniffing problems. The second one we've got is something called interleaved execution. This was introduced to alleviate the problem with multi-statement, table-valued, user-defined functions. The problem with them being that they're absolutely disastrous. We've got memory grant feedback. This is also SQL 2017, and this one is intended to solve the problem of query plans which request too much or too little memory and lock their requirements in with the plan and can't adapt. So that was 2017. Moving on to the new version of SQL Server 2019, currently in preview, we've got 3 more aspects of intelligent query processing. We've got the table variable deferred compilation. This is similar to the interleaved execution, but this time it's table variables, not the multi-statement functions. And this is intended to address the row estimation problems with table variables. We've got scalar function inlining, which is designed to alleviate the problems with scalar functions being absolute performance nightmares. And finally, we have something called approximate query processing. This is intended to help queries on really, really large tables where we don't actually need a correct value. We just need a more or less approximately somewhere in the right vicinity type answer. All right, so those are the 6 features which fall under intelligent query processing these days. And I'm going to go into these one by one and pull up demos of each one. So first up, adaptive joins. Traditionally, up until now, the decision as to what kind of physical join a query would use has been made by the query processor before any part of the query starts executing. The problem with this is if the optimizer has made an incorrect estimation in terms of the number of rows, its join selection is going to be completely wrong. It's going to pick up a nested loop join for large numbers of rows or a hash join for small numbers of rows. Neither of those is optimal in that situation. And so you end up with a category of problems called bad parameter sniffing, where the row count is misestimated, the plan is inappropriate for those row estimations, and the plan is bad until a new one is compiled. With adaptive joins, what happens is that the join type is not selected by the optimizer until the first input has been read. Now, the first input is only read during query execution. So in other words, the optimizer doesn't pick what the join type is. It simply says, I'm going to put a join here, don't know which one yet. And it allows the query processor, once it's read the first input, to pick what kind of join is used. We can't get merge joins with an adaptive join. The choice is purely a hash join or a nested loop join. And what the optimizer will do is when it generates a plan, it will estimate a threshold, what number of rows the loop join is better underneath, and what number of rows the hash join is better above. And then the query processor simply selects loop or hash join depending on what number of rows is read from the first input. So let me see if I can find some code here. So what I've got here is a SQL 2017 database, and I've got a stored procedure which reads from shipments table and shipment details table. There's nothing fancy here. It's just a master detail table. You might notice from the table name that this one is a column store. There's a reason for that. I'll get into it in a second. And then we filter by the client ID. Again, nothing fancy here. And if I go and change my compatibility level, sorry about this, bounce it down to 2016 and run this query, what I'll end up with is a nested loop join. The number of rows coming from my outer table is only 22, estimated 12.2, actual 22. My estimation isn't too bad. And in that case, I get a nested loop join. We flip my compat mode back up to 17. And now if I run this, I get a rather odd looking plan. I've got here something, firstly, that has 3 inputs into a join, which is something we don't typically see. A join is between 2 tables. And I've got a join type here called an adaptive join. So what's happening here is that the shipments table is my outer table. This table is getting read. It's got an actual row count of 22. It's got an estimated row count of 12.2, same as we saw before. If the row count is underneath the threshold, and it's not always easy to see, where's my threshold? There we go. The threshold is 1004.25 rows. 22 is indeed below that, so we've picked the index, the nested loop portion of the join. So that's this one. And you can see this one was picked because I've actually got a row count on there. If my row count was above that 1004, this branch would be taken instead. This is my hash join. We can see that was not taken because I've got an actual row count of 0. The nice thing about this is that the query processor, each time it executes this query, can pick which join type it likes based on how many rows come out of this, without needing to recompile the plan, without needing to fetch a new plan. So that is adaptive joins. So have we got any questions on adaptive joins? No
Doesn't look like
questions.
there were any questions now. Somebody's asking about making it a little bigger. Remember, you do have the zoom in the top of your window that you can use to make it bigger.
What's a little bit bigger?
Oh, I'm talking back to the person who asked. They wanted the screen a little bit bigger, but they have control over that with the zoom on
I can do that as well.
the window.
Okay, I will make things bigger. That's probably about as big as I want to go.
Let me see if I have a couple more questions, though. I think I've got to. Let's see. Scroll through this. It looks like. So the plan's still only compiled once, they ask. Is that correct?
Sorry, yes, the plan's only compiled once. Nothing's changed with the plan compilation. The plan is generated once. It's just generated with a join type that the query processor picks the join type rather than the query optimizer. Right. So nothing's changed in the compilation process itself.
I have somebody asking that's 2019, but that was 2017, correct?
This is 2017. The first 3 of these features are SQL Server 2017. The last 3 are 2019. So this one is a 2017 feature.
Okay. That looks like the questions then.
All right. Next, interleaved execution. If this was a live presentation, I'd be asking how many people have run into the pit trap that are multi-statement functions. But since this is not a live session, I'll just imagine a whole bunch of people groaning and complaining about this. Multi-statement, table-valued, user-defined functions are something that developers tend to love until they keel over and die and perform abysmally. I have seen a situation where the developers of an application decided they were going to attempt some form of object orientation in the database. Don't ask, really bad idea. But what they ended up having was an application that consisted almost entirely of multi-statement table-valued functions calling other multi-statement table-valued functions, passing around table variables, and calling still more multi-statement table-valued functions. To say this was abysmal was an understatement. This little application could not scale. At the time I encountered it, it was running on a 128 core server with half a terabyte of memory. The database was, I think, 150 gigs in size, and TempDB was nearly a terabyte and needed to be that size because of the implications of these functions. They asked me to fix it. It's probably I think this is the first and only time I've ever turned around to somebody and said, can't fix. Absolutely unfixable, throw it away and start over, because it's absolutely abysmal. The problem with multi-statement table-valued user-defined functions is that they return their data in table variables. Table variables cannot have their row count estimated unless you put recompile hints on, which you really don't want to do because that throws the CPU usage through the roof. If you don't recompile your plan, what you get, and by the way, I mean option recompile on the query that uses a table variable. If you don't do that, then you get a number of rows for the table variable estimated as either 1 or 100, depending on which cardinality estimator is in play. The new CE should be estimating 100 rows. This is not exactly ideal, because there probably isn't 100 rows. If there is, great, it'll be fine. If there's 100,000 on the other hand, well, congratulations, you've got a row count misestimation, and we know what row count misestimations do to the optimizer. Bad plans, bad performance, and all sorts of fun problems. So what's happened with interleaved execution, and this is also a 2017 feature, is the user-defined function is executed first. And then the plan for the query that uses the user-defined function is sent back to the optimizer for an optimization based on the actual row count of the rows in the table variable which the function creates. So we don't have any more problem of we don't know how many rows are coming out of this function, because we execute the function first and then only go back and execute the outer query. So we don't have this 1 row, 100 row variable row estimation problem that you get from table variables. And I should have one of these around here as well. Now, I'll caution you, these are very hard to see. They're actually very subtle. You can't, if you look at the execution plan, easily see that this is happening. And there's nothing you have to do in the query to make this happen. Now, it's actually quite good that there's nothing that you have to do in the query to make this happen. It's transparent, it just works. But it does mean it's kind of hard to demo because it's a little hard to see. Anyway, I've got a function here. Create or alter function. Shipments, join shipment details. Nothing fancy here. I'm doing some aggregation, I'm doing some filtering, and I'm inserting it into the table variable that returns my function's results. This is a fairly stock standard multi-statement table valued user-defined function. And this is roughly how it would be used. There's my function here. Now, firstly, I'm going to go back and switch my compatibility level down again, back to 2016. I probably should have scripted that out, but okay. If I run this on 2016 compat mode, there is my function, and I've got an estimated number of rows to be read, 100. Pretty classic. That's the optimizer's wild ass guess, because it's got absolutely no idea how many rows are in that table variable. it's estimating 100. Actual number of rows read 26,268. So my estimation is slightly off, and my plan is going to be rather inefficient. Not in this case, it's only 6 rows in the actual query, but if this was a real query in a real system, this would be kind of problematic. Right, so back to 2017 compat mode. And I'm just going to run this again. Nothing changes other than the compatibility mode. All right, table scan, shipments. The only difference here is that the estimated number of rows to be read is 26,268. The function was executed first, its results put into a table variable, then this query which used it was optimized based on the known actual number of rows in that table variable that came out of that function. And so my query is going to be more efficient. Again, in this case, I've only got 6 rows coming out of this thing, so you're not going to notice a big difference in the plan. But in the case of queries that run frequently, in the case of queries that use functions in other ways, you'll certainly notice a performance difference. Now, there is one problem with this. You'll notice I've joined to the function. This doesn't work when the function is part of an apply, because the optimizer has to know how many times this will run before it runs the query, because it's got to run it before it runs the query. And so it has to be on the right-hand side of a join, not an apply. If you're applying to the function, you're still going to get the old behavior and you're still going to get the old performance. Unfortunately, there's nothing we can do about that. It's just the way that the functions work. Maybe in the next version of SQL, we'll have another optimization on this. But for now, it only works if you join to the function instead of applying to it. So that is interleaved executions. Any questions?
So we have a question noting that both plans showed missing index recommendations, and would the performance have been affected by that?
Please ignore my missing index recommendations. My database actually has almost no indexes. No, I'm not demoing indexes. I'm showing just the adaptive query processing. If the index had existed, you'd have seen a slightly different plan, that's all. It's not going to be relevant to what I'm demoing with the interleaved executions. And no, it probably wouldn't have made any difference whatsoever. That was on here, actually. You'll notice it's on transactions. It's actually this index scan that is complaining about. Okay, so the third of the 2017 intelligent query processing features is memory grant feedback. The problem with memory grants is that they are selected at optimization time, as with pretty much everything we've seen so far, and they're selected based upon the row estimations. And again, if the row estimations are wrong, the memory grant requests are going to be wrong. So taking a step back quickly, memory grants are chunks of SQL's memory used for typically hash joins, hash aggregates, sorts. There's a couple of other operations which use them as well, but those are the offending 3 operations. They all need memory to work. The hash aggregate and the hash join needs memory to generate the hash table, and a sort needs memory to do its sorts. It's basically its sort. If the query requests too much memory, it's going to have to wait for memory, and that's going to limit the number of concurrent queries that you can have running. I mean, if you've got 100 megs of memory available for memory grants, and every query wants 20 megs, well, you're not going to get more than 5 queries running concurrently, which is a problem for throughput. On the other hand, if your query requests too little memory, it spills to TempDB because it needs that space. And this is really ugly. I've seen a query that spilt 5 or 6 times to TempDB, and horrible execution characteristics, absolutely horrible. I mean, we're using memory to avoid going to disk, so let's bounce our query through TempDB, which is on disk. This really doesn't work very well. But until now, we couldn't do very much about this. And this was always an area that was really hard to fix. If your query requested the wrong amount of memory, well, good luck. There were tricks you could play. There were silly things you could do with the query, cross-applying to structures which looked like they generated rows but didn't. Basically, they're all around tricking the optimizer into asking for more memory. 2017, however, SQL 2017 offers memory grant feedback. What happens here, and this is actually one of the intelligent query processing features which doesn't work on a single query. With the previous two, you saw me run a single execution and saw the query behaving in a certain way. But memory grant feedback works across executions. What happens is the first time a query runs with a memory grant, the query processor, after it's run the query, makes a note in the cached plan as to how much of the memory was actually needed. So if the query, say, requested 100 megs but needed 10, the query processor notes that the memory grant was too high. If it requested 10 and needed 100, the query processor notes that the memory grant was too low. And then on the next execution, the memory grant is adjusted. This normally requires a recompile. Normally, prior to 2017, your memory grants were fixed to a plan. If the plan requested 20 megs of memory, the plan requested 20 megs of memory, and it requested 20 megs of memory until it was thrown out of cache and recompiled. With this feature, however, the memory grant request can be adjusted after each execution to account for what was actually needed, not what was estimated. And this is saved with the plan's cache. Sorry, this is saved with the plan in cache. So until the plan is removed from cache and recreated, this adjustment of memory grant is kept track of. And this is one I was actually having problems getting a working demo on, so I will note an apology. This doesn't actually look quite as fantastic as it really is. So I've got a query that returned no data, but somehow my memory grant was really, really bad. And you'll note I've actually got a warning on my select. Warning, the query memory grant detected excessive grant. The grant size was 70 megs, but only 1.5 megs was needed. Well, I'm surprised 1.5 megs was needed because I've got a hash match on no rows. But that is what was apparently needed. And I think I've just broken things, so give me a sec, let me go and fix that. One of the problems with adaptive query processing is that it actually adapts. That here, I want to run that. That. So F4 properties. Memory grant info, and you can see here that it did request 70 megs of memory. There's plenty available. This is my desktop, but I'd rather a query wasn't requesting 70 megs of memory when it needs 1.5. If this was 2016 or earlier, when I run this again, I'd get a 70 meg memory grant again. This is not 2016. You'll note my warning has gone. And if I now go and look at the properties of this and go back into memory grant, desired memory, 5.2 megs. Required 4.2, max use 1.3. We're still off. We're still requesting far more than we need. We're requesting 5.2 megs when we need 1.3, but I think you'll agree that 5.2 where 1.3 is needed is a little bit better than 70 where 1.5 is needed. And I can run this as many times as I like, and this will now stay met on this value because it's within the threshold. It's not going to adapt again. To adapt again, my memory grant would have to be 10 times what I need, which it's not. It's about 4 times. And so I'm going to keep this memory grant until this plan is thrown out of cache. at which point we get a completely fresh plan, again with our 70 meg memory grant, but the second execution fixes that. So that's our memory grant feedback, the ability to adjust the memory grant per query after the execution to dial it into the actual amount of memory that the query really needed. Got any questions on this one?
You had one question about whether it kept adapting, but then you answered it in your.
It will kind of keep adapting until it gets within a threshold, and then it will stop. There is a pathological case where the memory grant requests the queries. Let's say we've got a query that wants a small amount of memory on one execution, large amount of memory on the next execution, then small. It's a really weird case, by the way. I've never seen it in reality. I can generate it. I've got a blog post on it. But it's a particularly pathological case. And in that case, the memory grant will always be behind what the query actually needs. Query execution requires high amount of memory. The adaptive, the memory grant feedback will set the next request to high, but the second execution needs low. In that case, it oscillates 32 times and then stops. So it won't oscillate forever. It won't adapt forever. Either it will dial in on a good value, which is within 10 times what's actually needed, or if the optimizer detects that it's oscillating, it'll stop after a certain amount of time. And at the moment, that appears to be 32. That is not documented, so it's completely subject to change.
Okay, and I've got some questions asking whether that's going to be pushed back to 2016 or 2014.
My gut feel is features will not be going back down the versions. This is a 2017 feature.
Mm-hmm.
If it was going to be backported to 16, it would have been done so by now. I don't see any of the adaptive processing features going back version. I just don't think Microsoft's going to do that. Feel free to upgrade to the latest version. It's really nice.
And then somebody asks if you have any idea what the formula is that they use to adjust the memory grants.
Do I have any idea of the formula? I do, and I'm not going to tell you because I know it's undocumented for a reason. These things are obligatory, undocumented. Microsoft reserves the right to change these without warning, notification, or anything else. Please do not depend upon them. I can tell you by basically trial and error what it is at the moment, but that means absolutely nothing because the next patch might change something. And Microsoft's been very careful not to document this stuff for exactly that reason. Okay, one additional note I need to make at this point for the 2017 stuff. You may note that some of my tables have said column store on them. That's just because I created a second table and put a column store index on. At the moment, in SQL 2017, both memory grant feedback and adaptive joins require batch mode. They require that the query is running in batch mode, not row mode. This is a 2017 limitation. Well, no, actually it's not. I'm slightly lying to you there. The batch mode limitation is a fixed one. These features only work in batch mode. In 2017, that means column store. However, one change has been made in SQL 2019 is that normal row store indexes, that's these things, can execute in batch mode. And once they can execute in batch mode, they can get the memory grant feedbacks and the adaptive joins without needing the column stores. But in 2017, it does require that the tables, or at least one of the tables involved in the query, is a column store so that you get the batch mode processing. At the moment, that's not going to change. So if you're not seeing this in your queries, you're not seeing it because of the execution modes. That's plain and simple what it is. All right, so that was our 3 2017 features. So very quickly, kind of quickly, since I've only got about 20 minutes left, let me take you through the 3 newer intelligent query processing features that are in SQL Server 2019. Now this is still in CTP, and I have, I'm actually not even sure which version I've got. 2019 CTP 2.3, apparently I've got an old version. We are up to CTP 2.4, but I'm using an older CTP here. These features all work in 2.3. They will probably work slightly better in 2.4, but for the moment, I still have 2.3 here. All right, so the first of the 2019 features is table variable deferred compilation. Now, cast your minds back about 10 minutes or so when I talked about multi-statement table valued user-defined functions. The problem with those things is that they put their data into table variables, and table variables can't have their rows estimated, and so we get bad plans. The 2017 feature, Interleaved Execution, fixed that for the functions, but it didn't touch the table variables themselves. 2019, however, adds in table variable deferred compilation. Currently, and this is 2017 and all earlier versions back to 2005, your table variables, when the optimizer generates a plan that has, for a query that has a table variable in it, it estimates the table variable to have a fixed number of rows. This is typically 100. On the new cardinality estimator, it's typically 100. On the older cardinality estimator, pre-2014, it was 1. But whichever it is, the estimation is this for a reason. It can't figure out how many rows are in that table variable. The row estimation and the plan generation occur before the table variable even exists, because their execution optimization is at a batch level. So the table variable doesn't exist, and so the optimizer can't figure out how many rows are in the table variable, and so it guesses. And it guesses at 100 with the new CE. With table variable deferred compilation in 2019, what happens is that the query which uses the table variable is not compiled. It doesn't have a plan generated as part of the rest of the batch. Instead, the rest of the batch runs, the table variable is created, the table variable is populated, and then when the query that uses the table variable starts to execute, it is compiled at that point only. The compilation is deferred until the point of execution. What this means is our table variable, we know how many rows are in it. The optimizer knows precisely how many rows are in it because it can actually look at the table variable and see exactly how many rows are in it. And this, to be honest, looks very similar to our interleaved execution. That is scalar functions. That's not what I want right now. Table variable deferred compilation. Okay, so I've got a table called important clients, and I'm populating it well. I hope if you're doing something like this, you've got a better way of selecting your important clients than randomizing them by new ID, but I've been lazy and that'll do the job fine. And then I've got a query here which is using my table variable. So let me start by making sure my compatibility level is 2017. If I run this and I go and look at my execution plan, my table scan for my important clients table has an estimated number of rows to be read of 1 and an estimated number of rows of 1. I'm honestly not sure why it's 1 and not 100. I would have expected the new CE to be in play here and give me an estimation of 100 rows. For some reason, I've got 1. I don't honestly know. It's something I want to poke at a little bit. But either way, 1 row is wrong. 100 rows is also wrong. There are 347 rows in this table variable. If this query was larger and more important, this would have a fairly significant effect on performance. But even now, as you can see here, if we look at our nested loop join, we can see that it processed 3,162 rows of 9. Whoops. running joke about percentages notwithstanding, what's happened here is that the nested loop estimated that it was only affect 9.07 rows, but it actually ran for 3,162 rows. If anybody can spot a classic bad parameter sniffing problem here, yep, it is exactly what it is. On a larger row count, this would be highly inefficient. This should be a hash join on larger row counts, but it will be a nested loop join because the number of rows coming out of this is estimated at 1. So let's fix this. On 2017 and below, the only way we'd fix this is by putting an option recompile on that query, which we typically don't want to do because that means we're recompiling the plan on every execution. I'm just going to set my compatibility level to 2019, and I'm going to run the whole thing again. The query plan shape hasn't changed, but if you look at the numbers, they definitely have. Table scan of my table variable, estimated number of rows, 347. It knows there are 347 because the compilation of this query was deferred until it's the point of execution, at which point our table variable was populated. My nested loop estimation is still wrong, but it's now wrong in the other direction, and it's wrong by a fairly small margin. 2,994 of 3,149. I can handle 150 row misestimation on a loop join that's affecting 3,000 rows. This is not going to have a significant effect on my query's performance. This estimation is close enough to be good enough. And that's solely because my table variable has been estimated, has had its row count known at compilation time instead of been estimated at 100 rows as we'd see in the older versions of SQL. So that is table variable deferred compilation. Any questions on this one?
Doesn't look like we have any questions on that one yet. So.
Cool. It's pretty similar to the function, so I'm not overly surprised. All right. The one that I am absolutely rejoicing over, this is fantastic. Scalar function inlining. I'm certain that somebody in the audience has encountered the case of they put a scalar function on a query and suddenly performance goes into the basement, if you're lucky, if not worse. Because scalar functions are absolutely horrible. I affectionately refer to these things as developer pit traps, because developers I know keep running into these at high speed and then coming whining that the performance isn't what they expect. No, it's not. Scalar functions have been absolutely horrific ever since they were introduced, and that's in what, SQL 2000? 2005? Somewhere way back there. When? I think it was 2000. The problem with scalar functions is that they run once per row. Now, that's a problem on larger row counts. It's especially a problem if the scalar function does any data access, because that data access happens per row. And so you can dump a function into a query and see a performance degradation of several thousand% without anything else needing to be done. It's a lovely way to slow a query down. I mean, if you want to write something slow so you've got options for optimizations later, scalar functions, at least until 2019, is a lovely way of doing that. I really don't recommend that, though. 2019 allows certain types of functions to be run inline. They're not run as a separate batch. They're not run in a separate execution context. They are actually inlined into the query and executed with it. And fortunately for all of us, this is not a very, the limitations on this one are actually quite lax. Any function that has a select or set in it is probably okay. If it does data access, it's fine. If it's got if and else branches in it, it's fine. The only things that don't work are things like getDate because they're non-deterministic. There are some complicated query processing constructs you aren't allowed. I do recommend consult the documentation, but you're probably going to find that most functions will simply go inline without you needing to do a thing about them, which is absolutely lovely. So back to my 2019 server. I have a very simple function here called dateOnly. Oh, I'm sure so many people have seen this because it's easier to do this in a function than to put this into every single one of your queries. Now, I've got a blog post on this. No, I've actually closed my browser, but I've actually got a blog post on this where I showed that running this in a query with, I think, a couple million rows returned in 100 odd milliseconds, but running the function in the same couple million rows took 3.5 seconds to execute. It really can be that bad. Right, so let me go switch my compat mode back down to 2016 and run my function. And this is probably what you expect to see from a scalar function. We've got a compute scalar. And if we go and look at the properties of this compute scalar, you can see that we have dbo.date only of the transaction date. Now, what's happening here is that this function is being executed 31,467 times. It's not at all obvious from this, which is the other problem with scalar functions. But if I fired extended events up and ran this query again, you would see this particular function having a SP complete event firing 31,467 times. That's why these things are as intensive as they are. And let me just do some measurements quickly. Shouldn't type in demos, shouldn't type in demos. All right, execution plan off. Now this isn't too bad, but do keep in mind this is only 30,000 rows. I'm just going to turn my execution plan back on and switch us up to 2017. Sorry, so to 2019 compatibility level. It doesn't look all that different, although the row count's vanished off here. No big deal. Let's have a look at this. My function is now the date add, date diff contents of that function. The function itself has been inlined into the query and executed as a single batch. If I ran extended events at this point and ran this query, I'd have one execution completed for the query. So has that done anything for the performance? I certainly hope so. I didn't try this earlier. This could backfire. Yes, of course, that function already exists. So let's ignore that. 140 milliseconds to 46. The elapsed time is going to be the time to display this. It's not the time to execute it. Yeah. That's what you get from inlining the function into the query on 30,000 rows. On a few million, it would be a lot more dramatic. So that's scalar functions, scalar function inlining, which absolutely has to be the feature of 2019, if there is one. Any questions on this one quickly?
One question, would the rows in the query plan give an indication of how many times the function was executed?
The function is always executed once for every row in the query. So if I switch my compat mode back to 2017 and run this, this query returned 31,467 rows. That means this function ran 31,467 times, minimum. It might have run a couple more times, especially if there was parallelism involved. But at minimum, this ran 31,467 times. Ugly as hell, which is why this is an absolutely fantastic feature. Okay, so that's the only query. The one last one, this isn't all that impressive unless you're doing really large data warehouses and you need really large queries run against them. If anyone's ever tried a count distinct over a large number of rows, you know just how unpleasant that is. So 2019 has also introduced something called approximate query processing. This is nowhere near as sexy as inline scalar functions. And to be honest, I can't really see myself using this very often, but I did need a 6th item to pad out my nice 6 features, and so this one certainly counts. And it is actually under the guise of intelligent query processing. So this is necessary when speed is more important than accuracy, when you want a count distinct which is good enough. It doesn't have to be accurate, just close enough, please. The current guarantee is that it will be within 2% of the correct value 97% of the time. If there's any statistics majors in the audience, they're probably laughing right about now, but that's how we talk about this kind of thing. So it's 98% accurate 97% of the time. This is not intended for row tables with a few 100,000 rows. Unfortunately, I only have tables with a few 100,000 rows in, and so I can only show you that it works, not really show you how much more efficient it is. Let me just turn my stats time on though. I might be able to get something interesting out of this. No. Never take time at estimations with the execution plan on. No, they're pretty close, but again, this table's got a few 100,000 rows in it. I might actually be able to change it. Again, this really isn't the kind of database that this was designed for, so I'm really going to have trouble showing you much of a performance difference here. And in fact, the count distinct is way faster. I'm pretty sure that's not what it's supposed to show. We will forget about that for the moment. But if we look at the execution plan, you can... Let me see if maybe the... no, that was not what I wanted to do. And I don't have my column store indexes in here. It just changes back to what it was. Nothing majorly interesting in the execution plan here. This one doesn't have the hash match and then the stream aggregate. And it is apparently slightly faster, 38% opposed to 42. But again, this is really not the kind of tables this was designed for. Shipments has 31,000 rows in it. This is designed for tables with millions of rows. And so, yeah, I'm really not going to be able to demo it very well here. But what this is, essentially, it's more or less accurate, and it should, on larger row counts, be much, much faster than a full-on count distinct. All right, so that's the last of the intelligent query processing features. The 3 that are in the 2019 release, the table variables and the table variables, the inline scalar functions, and the approximate query processing, they don't require batch mode. They run fine in row mode. As you saw, I didn't have column stores involved. Okay, so we are pretty much out of time. So do we have any remaining questions on anything I've shown so far tonight?
All right, we do have one person saying, would you recommend waiting for 2019 if they're already in the middle of a plan to upgrade from 2014 to 2017?
Oh, that's tough. That's really tough. We don't know when 19's coming. We're at CTP 2.4 at the moment. We haven't had a release candidate. Really, this is going to depend on how far you are in your testing. If you've just started evaluating for 2017, maybe hold off. Gut feel it won't be more than 6 months. But, well, we've only got 9 months of 2019 left, so it's got to be within 9 months. Gut feel we'll probably see it sometime August or so. That's a complete guess on my part, please. I don't have any insider knowledge on that. It's really going to depend on whether any of the 19 features are must-haves for you. Have a look at what's new in SQL 2019 and see if any of the features are ones that will help you, or ones that you can't live without, or ones that will make your life easier. If you, for example, you've got scalar functions all over the place and you've got problems with them, maybe wait to 19. If you don't, have a look at the other features. I can't answer that for you. It's a really hard question.
Okay, and then I've got, going back to the inline functions, is there anything in the select operator that shows the function calls?
And the problem with the inline function is that it's never been shown in the execution plan, which led people to believe that it wasn't a performance problem. You cannot, from the execution plan, tell that the scalar function even exists. And that's the 2017 and earlier. That's one of the reasons there's such a performance problem, is that you can't see their misbehavior from the execution plan. With the 2019 inlining, the function doesn't exist. The function's replaced during parsing, so by the time the optimizer gets it, it doesn't exist at all. And so no, there's absolutely no evidence left in the plan to say there was a function, because as far as the optimizer is concerned, there wasn't a function. It's going to make things a little harder to debug, probably, but I'll take that over the performance nightmare those things were beforehand.
All right, and that looks like all of the questions. I've got several thank yous to you, Gail.
Okay, thank you. That was fun.
All right, and coming up next, stay tuned for our next session. My company is going to Azure. What can I do? With Paresh Matawala.
Run. No, kidding. Embrace it. It's awesome.
Thank you all for attending. This is 24 Hours of Pass.